Alright, you physics freaks. I'm here to give you a quick tutorial on how to work with this virtual lab setting for this acceleration, net force, and mass lab. The virtual lab setting calls it Newton's Law Lab, which it is, but um, I have a different name for it. It doesn't really matter what you call it. But anyways, here's the setup. And what you have is you have this hover disk. You have this person pulling the hover disk with a vernier force sensor, just like the ones you have used in class. And then you can change the hover mass to different masses. And you really don't get a choice. You just got to go with what they give you with the arrows. And the one thing I do want to point out about mass is it shows it in grams here. I would like to see it all in kilograms. It will make it easier when we talk about the numbers later. So 1,250 grams is 1.25 kilograms. And then if I want to change the amount of force, the net force on it, I can just move the arrows side to side and it gives me various forces, and I can do that. So you will run two different experiments. One is acceleration versus mass, and that's where you just change the hover mass and keep the force strength the same. And then the other experiment is acceleration versus net force, and that's where you will change the force strength but keep the hover mass the same. So I did explain that briefly in the assignment that I've posted, but that was important enough to mention it again here. Now, the reason that this hover mass or this hover disk accelerates is because it's getting pulled by this force sensor. And it's getting pulled to the right by the force sensor. This person's pulling with a constant force. In doing so, this constant force that the person pulls makes the hover disk accelerate because the hover disk is frictionless, which means there is no force going to the left. So all of the force is going to the right. And when you have more force in one direction than the other, and more specifically in this case, all the force in one direction and none in the other, you have what is called a net force, and that's what causes acceleration. And so we want to find this relationship of how much does your acceleration change as you change the amount of force you pull it, and also how much does your acceleration change as you add or take away mass from the system that's being pulled. In this case, the system is your hover disk. All right, so I'm just going to set this at 1,250 grams, which is 1.25 kilograms, and I'm just going to have the force set at 1.6 newtons, and I'm going to start the data collection, and I want to show you how you get acceleration, because that's probably the most difficult part of this. So I press start, and whoopee! There you go. You can see the hover disk speed up. It accelerated, so that's fun. Now, this is how you get acceleration. You are given two graphs down here. You have a position graph, which you could find acceleration from, but that's not very fun because it's a curved graph. Now you have this velocity graph, and this is the graph to go to for acceleration. Why? Because you have this nice linear slope, and this nice linear slope means you have a nice constant acceleration because the slope of the velocity versus time graph is equal to the acceleration of the object. So let me show you how I would get the slope. I would probably start down here, and I have a point down here of 0.6 for my time and 0 for my velocity. Now I'm going to find a point on this line that crosses a grid line, a good grid crossing, and I want to do it as far away as possible. And it looks like the line crosses here at this point. This is a nice good crossing grid. We have 1.5 seconds here, and we have 1.2 meters per second. So now if I were to calculate that slope, my rise would be from 0 to 1.2, so my rise would be 1.2 meters per second, and my run would be from 0.6 to 1.5, and so that would be 0.9 seconds. So I would take 1.2 meters per second divided by 0.9 seconds, and I would get some number. I don't have a calculator with me, and so you can calculate that yourself, but you get the drift. So once again, it would be 1.2 meter per second rise divided by a 0.9 second run. So it's 1.2 meters per second divided by 0.9 seconds. That is the acceleration for this one setup here. So then you'd have to do it again with a different force. If you're doing the acceleration versus net force experiment, do a minimum of 5 different forces. And then you'd have to do the same thing for 5 different hover masses. And once you have that done, you can do more than 5 if you want, but minimum of 5 is fine. Once you have that all done, you have your data for 2 different experiments. So you'll have to come up with 2 different graphs, 2 different mathematical relationships, basically 2 different conclusions. You should get really good correlations for this graph. Don't be all excited that you got this great correlation. The data that you get from this computer simulation is based off of good mathematical formulas that the computer program uses. So you should get really good data. If you don't, you've probably calculated your slope wrong or something like that, and so you may want to redo it. All right, so I hope this was helpful, and good luck doing this lab over the next day, Friday, and also another day, Monday, when will either be virtual or we will be together. I have no idea. It's Thursday night. Nobody's come out to tell me anything about our COVID life at Hill Murray. So, whatever the case may be, I will see you someday. Check you later, people.